Dear ladies and gentlemen, dear organizers, thank you very much for this chance to present our research results in such extraordinary situation. I'm presenting work which was performed in the Institute of Physics of the National Academy of Science of Ukraine in Physical Electronics department. Also, two of my colleagues work and study in Taras Shevchenko National University of Kyiv. The topic of this presentation is a mesoscopic self-ordering in the 2x1 cerium on molybdenum 112 substrate nanostructures. And just before we will start, I want to say, greetings from Kyiv. There are a few postcards of our beautiful city. And let's come back to the motivation of our research. Investigation of the structure of adsorbed films on forward substrates, such as the 112 phase of the tungsten and molybdenum crystals, revealed a rather long-range indirect interaction between the electropositive atoms through the substrate electrons. The specific anisotropy of this interaction creates adatomic structures which consist of linear chains crossing neighboring substrate furrows, and these chains are arranged at nanoscale distances from each other along the furrows. For example, strongly electropositive alkali and alkaline earth metals on the 112 surface of tungsten and molybdenum were found to form chain-like structures, primitive n by 1 in the submonolayers coverage range, where the n, which is the number of substrate periods, reaches the value of 8, what means that the interchain distance is about 2 nanometers. However, in the case of adsorbates with more complex external electron shells and smaller polarities of the adsorption bonds, such as rare earth metals, such long-range indirect interaction through the electrons of the substrate has apparently a smaller effect on the structure of the film than the short-range interactions between the atoms. Indeed, among 5 studied rare earth metal systems, the stable linear chain-like structure with a long period have been observed only for ytterbium. For the gadolinium on molybdenum 112 system, chain-like structures were not detected at all. The chain-like structures of 3 other systems turned out to be metastable. They lost the long-range order after their annealing at some higher temperature and subsequent cooling to lower temperature. It was suggested that such operation results in formation of a surface alley between atoms and surface atoms, which solidifies as a surface loss due to fast decreasing of atom mobility with temperature. This actually can mask the processes of add-film self-organization and motivates further research of ordering conditions in the rare earth metals add-films on the forward substrates. In the present work, we studied the atomic structure and the work function changes in the process of cerium submonolayer growth on the molybdenum 112 surface. The molybdenum phase 112, which was used in our study as a substrate, is extended surface, which consists of furrows altered by ridges. The high anisotropy of this surface, as well as molybdenum refractory properties, made it highly attractable as a sample for surface science studies. Actually, this research is a logical progression of previous studies of bimetallic surfaces performed by our group during the last 20 years. Particularly, it was already mentioned alkali, earth, rare earth metal adsorbate systems on molybdenum. The results of one of them is shown on the figure. It's lithium chain-like structure observed on the molybdenum substrate. It can give you some idea about the visual appearance of chain-like structure we discussed on the previous slide. From the practical perspective, cerium compounds found wide utilization in the numerous industry. The bright examples of such applications are thermochemical two-step water splitting process, water-gas shift reaction used in manufacture of ammonia, hydrocarbons, and methanol, antibacterial therapy with nanoceria nanoparticles. Thus, the study of elementary film formation process can be beneficial for development of new materials or designing the new nanoscale systems. All our experiments were performed in a rebar ultra vacuum chamber. We utilized three methods for the surface state characterization: low energy electron diffraction to define the surface structure, electron spectroscopy for elemental composition analysis, and contact potential difference for measuring the work function changes. The molybdenum 112 sample was prepared as a plate and was equipped with a spot-welded thermocouple. Inside the chamber, the sample could be cooled with liquid nitrogen down to 78 Kelvin and heated resistively and by electron bombardment up to 2300 Kelvin. The sample surface was thoroughly cleaned by means of oxidized anneal treatment. An atomic beam source of cerium consisted of a small piece of cerium metal attached to a tungsten wire heater by vacuum melting. The cerium coverage was defined as a ratio between surface concentration of cerium atoms and surface atoms of molybdenum 112 phase. The coverage value was considered to be proportional to the cerium deposition time. This rate was calibrated based on the analysis of some simple lead patterns as well as work function values. Due to extremely high oxidability of cerium, some remnant of cerium oxide could be present in the source. As estimated from joint Auger spectroscopy and lead measurements, oxygen part in cerium deposits reach from 1 to 25% in various experiments. Deposition of cerium and measurements were mostly carried out at room temperature. During cerium deposition fulfilled at room temperature, the lead patterns evidence the formation of predominantly two-dimensional overlay with primitive 2x1 structure from the early stage of absorption and throughout the submonolayer coverage range. Deposition of submonolayer amounts of cerium resulted in appearance of additional half-integer order diffraction spots along the 1,1-1 direction. The real space models interpreting primitive 2x1 lead patterns is presented below. Further coverage increase led to a gradual attenuation of both integer and half-integer order beams, which totally disappeared at cerium coverage about 1.5. The contact potential difference and Auger electron spectroscopy measurements indicate the consistent results and complement the lead observation. This graph shows the coverage dependence of work function difference relatively to clean molybdenum surface, cerium Auger peak amplitude, and parameters of the half-integer order lead spots, namely the intensity and full width and at half maximum. It seems that work function difference, Auger amplitude and intensity at first rise linearly with the coverage increasing. Then with coverage exceeding 0.5, which is the stoichiometric for the primitive 2x1 structure, work function is stabilized while, let me show you, that's stabilized and, Auger amplitude continues growing and intensity of lead patterns decreases. Taking into account that coverage 0.5 is a stoichiometric, as I said previously, the described changes of overlayer properties can be interpreted as evidence of the formation of a first-ordered cerium monolayer, over which a disordered second layer grows. However, the first primitive 2x1 monolayer is not perfectly ordered. Indeed, ordered parameter half-width never reaches its possible ultimate minimum value, as well as its lowest attained value falls at coverages exceeding the stoichiometric value of 0.5. Sorry, I'll come back. So here you can see that it does not reach the ultimate value. Obviously, the structure of the overlayer deposited at room temperature is not balanced enough and contains numerous defects, including possible oxygen impurities. Okay, let's go forward. Structures formed during the room temperature deposition are likely metastable due to the low adsorbate's mobility. Therefore, to activate ordering in the overlayer structure, we anneal the sample at gradually increasing temperatures in the range from 300 to 1400 Kelvin. At the annealing procedure, the sample had been kept for 10 seconds at the annealing temperature and then slowly cooled down back to the room temperature. Exceeding the 1400 caused partial desorption of cerium, evident from an abrupt decrease of the cerium amplitude and walk function difference values. This figure presents examples of variation in walk function difference, amplitude, and half-widths caused by annealing at constant coverages, which are less than 0.5. No substantial changes in amplitude and walk function difference are seen until the start of desorption. Therefore, and we see that it's quite stable here and here. Therefore, annealing at temperature from 300 to 1400 Kelvin causes no changes in the coverage degree. The earliest manifestation of annealing effect on the odor in cerium films is revealed in sharpening half-integer lead spots. The main ordering in the primitive 2x1 lattice occurs within the interval from 500 to 1000 Kelvin. At moderate annealing temperature, the ordering across the furrows proceed markedly easier, as you may see by relation between half-widths in direction of -1, -1, 1, it's a solid line, and -1, 1, 0, it's a dashed line. The spot anisotropy, and thus a direction-sensitive deviation from order, is more expressed at lower coverages. It persists even up to the highest temperature annealing in the coverage range less than 0.4. The anisotropy of half-integer order spots is clearly visible in patterns A, B, but completely disappears in pattern C. Another significant results of annealing for coverages less than 0.5 was revealed in the range of annealing temperature which are greater than 1200 Kelvin. The satellites appear on both sides of integer order lead spots as indicated by arrows. Notice that the half-integer order spots continue to exist. According to the literature, features of this kind reflect the emergence of some mesoscopic superperiodicity on the surface. In our particular case, this is one-dimensional periodicity along the 1, 1, -1 direction within the primitive 2x1 structure. Judging from the delta value, satellite splitting relative to the integer order spots, the mesoscopic period N amounts to about 24 substrate lattice units, which is about 65.5 angstrom. Since the primitive 2x1 cerium-molybdenum 112 phase grows by the first order transition, as there are islands occupied by the cerium film and areas of empty surface, such a mosaic surface with different intrinsic surface tensor. They are unstable to the formation of elastic stress domains. We suggested the formation of the one-dimensional mesoscopic superperiodicity observed by us in the primitive 2x1 overlayer is caused by the pointed elastic interaction. Evidently, the availability of sufficient areas free of adsorbate is an important condition for mesoscopic self-ordering. The coverage grows about 0.25 results in sharp increasing of the size of mesoscopic domains and eventual their disappearance. So it's reasonable to consider that the necessary free area amounts to about 50%. This corresponds to the alternating arrangement of free area strips and adsorbate stripes of N equal to 12 widths with internal primitive 2x1 ordering given in this model. As was already pointed out above, the half-integer order spots are rather broad along the 1,1-1 direction, indicating the presence of disorder. It's a natural consequence of a translational degeneracy of the primitive 2x1 lattice along this direction, namely two equivalent positions of the unit cell of this superstructure can exist, and both are present within the stripes here. Consequently, that layer consists of two equivalent domain types separated by domain walls, dashed lines. Similar mesoscopic self-ordering was earlier observed in the oxygen on cuprum and nitrogen on cuprum systems. As one of examples, you can see this scanning tunnel microscope images of oxygen superperiodic structures on cuprum, taken from the article of Kern et al. Coming back to our annealing temperature dependence, we can see a rather sharp emergence of superperiodicity with period of 24 substrate cells at annealing temperature about 1200 Kelvin for coverage 0.22. And it indicates that this temperature is critical for an irreversible transition for the simple primitive 2x1 phase to one-dimensional mesoscopic structure. Similar values of period and critical temperature were observed for all coverages less than 0.25, with coverage 0.1 being the lowest coverage at which spot splitting was visible. Annealing in the range of coverage from 0.5 to 0.75 resulted in significant changes both in surface structure and the walk function. Instead of the primitive 2x1 structure, new adatom arrangement appear, showing a denser compression inside the furrows. Here you can see lead patterns which are attributed to incommensurate centric 8x4 and centric 1.44x2 lattices with stoichiometric coverages of centric 8x4 and the centric 1.44x2. Stoichiometric coverages of 0.625 and 0.7 respectively, suggested hard sphere models of corresponding submonolayers structures are shown below. Please note that they have not been validated by any kind of simulation, so this is a tentative suggestions compatible with lead patterns. One of them, centric 8x4, has been observed in coexistence with primitive 2x1 in the coverage range from 0.5 to 0.63, indicating the first order transition. You may see that here in this range, both structures exist. Another structure, 1.44x2, has been detected as a single phase that undergoes continuous uniaxial compression along the furrows during coverage growth. The compressed phases are characterized by higher values of the walk function. That's lower difference in walk function than the primitive 2x1 phase. This actually reflects the depolarization of electropositive atoms during compression of the end layer. The splitting, we were talking about the splitting in our mesoscopic domains, became smaller with growth of coverage, and corresponding periodicity became larger as exemplified by this graph. We could distinguish these satellites only in the coverage range from 0.1 to 0.4. As a conclusions, we can say that the study of the walk function changes during growth of the cerium-molybdenum 112 at layer has testified that cerium atoms possess a dipole moment about 1.6 dBi, stipulating noticeable dipole-dipole repulsion between atoms. The investigation of atomic structure of cerium on molybdenum-112 has not detected the formation of long-period chain-like structure. Instead of that, growth of the primitive 2x1 layer has been found at the earliest stage of adsorption. This indicates lowering significance of long-range direct interaction between Z atoms and growing importance of short-range indirect interaction, competing with dipole-dipole interaction as compared with alkali metals and alkali earth metals on molybdenum. A mesoscopic scale, about 60 filestram self-ordering into a nanostrip array, has been detected in the broad range of the primitive 2x1 cerium on molybdenum overlayer growth, evidencing an importance of the elastic interaction in the formation of the electropositive at films. In addition, I want to say that this work was supported by the National Academy of Science of Ukraine, and thanks everyone for your attention, and I'm looking forward for your questions.
Okay, thank you, Dmytro, for your talk. Now the paper is open for discussion. Well, let me ask a short question about the dipole-dipole interactions. So in work function, you talk about the energy needed to extract electron from the Fermi level to the vacuum level, yeah? So
Yeah.
by depositing cerium on the surface of molybdenum, you are saying that cerium has a lower work function than the molybdenum. This is why you have minus 2 electron volts, for example, for the thickness of 0.5, for the coverage of 0.5.
Yeah, that's correct.
Is this my understanding? Okay, so the cerium, metallic cerium, has lower work function than molybdenum. And
that's so the deposition of cerium and molybdenum decreases the work function. I don't remember the exact value for clean cerium. So we are talking about bimetallic surface. So it's a mixing of atoms which gives us a new value of work function. Actually, so the cerium can demonstrate some different work function.
So the pure metals, eventually they will demonstrate just the intrinsic work function because of the position of the Fermi level, yeah?
So when we're talking about the surface, it's always mixing of atoms, and there are several main factors which actually defines this work function. And like the nature of atoms is only one of them, another is structure of the surface. So when we change in the structure, so we can imagine that this is rather, as I said, extended surface of the molybdenum. And when we add some cerium atoms, it actually changes also the surface roughness, and it also affects the work function, not only nature of atoms and atoms interactions.
Can you tell me how local your measurements of work function? For example, you have a plate of your sample, and then you deposit cerium on top. You measure work function as a local property or as a general property of all the surface?
It's a general property. We use an electron gun. And it's actually this contact potential difference methods based on the vacuum diode.
And all your plate is uniformly covered by cerium?
We cannot say that it's uniformly covered. It's it should be.
Well, I mean uniformly in as much as you presented on this schematic crystallographic.
Most of the surface covered uniformly, but I guess it's on like on border. It's can be slightly different. So we have other publications about the profile of our deposited films, but we here we assume that this is uniform surface, uniform film.
And well, the last question before we start with the next talk. You are saying that there is some kind of interaction between the cerium atoms which result in a change of dipole moments on the surface.
Yes, correct. So let me, if we're talking about the process,
yeah, this thing. So at higher thickness, you eventually get a more positive work function difference.
Yeah, so here we have a new structure formed as a result of annealing, and this structure is more dense than primitive 2x1 observed at first. And it's a well-known effect when more dense structures demonstrate the lower dipole moment. Am I answering you?
The lower?
The lower, yes. Actually, this like dipole moment can be derived as a first derivation from graph of our work function. So here we see that this dipole moment is quite large and then it decreases.
So it looks like it changes the sign because the work function difference goes up, yeah?
Yes, but our absolute value, or let's say absolute value, become larger with like this increasing of coverage, and then it decreases. And this indicates that our dipole moment decreases as well.
Mm-hmm. Well, it's quite interesting, yeah.
It's about 1.6 dBi for the P2x1, and as I remember, it's 1.4 for this centric 8x4 structure.
Okay, thank you, Dmytro. Thank you for your talk once again.
I can try to explain it in some simple model.
This was just my curiosity about the work function.
Okay.
Mm-hmm.
Thanks everyone again.
Okay.